Okay, welcome to Geometry, Arithmetic, and Differential Equation of Periods. Today we have Emenuel Scheidegger, who is going to talk about attractor points on the moduli space of Calabi Yau threefolds. So, Emanuel, please.
Okay, thank you very much, Hossein, for giving me the opportunity to present some work of mine in your seminar series. So I'm going to talk about a special kind of points in the modular space of Calabi Yau threefolds, and it's based on work with Kilian Böhnisch, Albrecht Klemm, and Don Zagier. So here you can see the overview. So I'm hopefully getting to the examples, and we'll see. So let me start with the geometry of modular space of Calabi Yau threefolds. So I want to review a few basics which I need in order to formulate the problem we're interested in. So we start with a family of smooth projective Calabi Yau threefolds of fixed diffeomorphism type. And then what we get with that is an associated polarized variation of Hodge structures. So we get a local system, we get a Hodge filtration, and we get a polarization. Polarized variations of Hodge structure. And this comes with a canonical flat connection known as the Gauss-Manin connection. And of course, if we look, since it's Calabi Yau, if we look at the highest part in the Hodge filtration, we get a line bundle, which is known as the Hodge bundle. Now, the crucial point about Calabi Yau threefolds is that M carries the structure of a so-called projective special Kähler manifold, and this structure is central to everything that's happening on this modular space. But today I only need part of it. So first we observe that sections of L are just nowhere vanishing holomorphic 3-0 forms. Which I will call omega. And then we have the Hodge-Riemann bilinear relations, which imply that the quantity omega bar, which is defined to be I times the integral of omega wedge omega bar, it defines a Hermitian metric on L. But we can view omega not only as a section of L, we can also view it as sort of a function on a local charge in N. So view omega as local function on M. Then what we get, since this is a metric, it's positive and it's just a number, so we can write it as follows. And in this way, we get a function on M which defines Kähler metric. Which I call Gij bar, and as usual, it's defined as di bar of K. This is known as the Weyl-Petersen method. Now, if we study locally the deformations, we can apply Cotera-Spencer theory. And this implies that the tension space at the point S in M is isomorphic to H21 of XS. And combining everything, we get a basis for H21, which is usually denoted chi, which is given by e to the k over 2 di omega minus di omega bar over omega bar omega. So the second part is just the projection of di omega to the H21 part. And as an aside, it follows by a simple calculation that then the metric can be written as this. So these last couple of lines are due to Tien. And then in principle, one could go on and take further derivatives of the metric. And then one obtains an expression for the curvature of this metric, which is very special. And in physics, this relation for the curvature is usually taken as a definition for what is meant by projective special Kähler. But we don't need this relation today, so I'm not going to discuss this. But when Hossein invited me to talk here, he said something like I should talk about physics. So let me do that. But of course, I can't say too much about physics because there's a lot of things that would need to be explained, and that's very difficult. So in physics, let's look at what is called an n=2 supergravity theory. And we need to specify a few things with H21 of X, so-called vector multiplets. And they turn out to parameterize the universal cover of the moduli space of a Calabi Yau threefold. Now, vector multiplets are a collection of fields with definite transformation behavior in. So maybe I should say that this is on Minkowski space R13. So a certain transformation behavior with respect to the Lorentz group of R13, and one part is that there are scalar fields in these vector multiplets, and they define a nonlinear sigma model. of my C maps C from R31 into the universal cover of M. So this is, as the name says, it's a gravity theory. So we want to know what solutions there are, and it's from general relativity maybe that there is a special sort of solutions, so-called black hole solutions. So one can look at black hole solutions here as well, and as usual. In the beginning, one makes a lot of simplification or a lot of assumptions to simplify the problem in order to have the chance to find it. And it's the same as in general relativity. The simplest case is that you look at static solutions, so not time dependent. You want them to be spherically symmetric, which reduces the problem essentially from 4 to 2 dimensions. Black hole solutions. But since we're in a supergravity theory, we have supersymmetry, so we also want to require that we have supersymmetry, that the solutions are supersymmetric. So they preserve some of the supersymmetry. Now, such solutions are characterized by a few quantities. Namely, first, they carry an electric and magnetic charge, gamma, which turns out to be in the lattice of 3 cycles of the Calabi Yau threefold. Then they have a mass. And the best way to describe the mass is by looking at its square, and this turns out to be the norm squared of a function which depends on the electric and magnetic charge and on the point in the nonlinear sigma model, where C gamma Z is defined to be, in physics it's defined as the periods of omega along a cycle represented by gamma multiplied by e to the k over 2. This has the name as so-called D-brane central charge function. And so this is really a function on the universal cover. And now what physicists have observed, so these were, now I forgot the names, Carlos, okay, of course, Ferrara, Carlo, Strominger, in '95, they observed the following. I'm essentially only telling the outcome. So there is a particular gradient flow on M twiddle, which is called attractor flow. Given by the equation mu dd mu set A E is minus Gi bar d bar j bar, and then the potential of the gradient flow is just the logarithm of the absolute value squared of the D-brane central charge function. So that's the gradient flow that characterizes these black holes. And what it essentially says is that, so first of all, it's claimed that it has a fixed point. And these fixed points which I often denote by C star of this flow, are called attractor points. And essentially, what it says is the following, that if you're looking at these black hole solutions, since the theory depends parametrically on these scalar field sets, you could ask, if I fix the charge and the mass, how do the solutions depend on the scalar field set? And what they observed is the amazing phenomenon that no matter where you start looking your solution, it will always they will always flow to the same points, and these points are uniquely determined by the charge. So that's how attractor points were originally introduced. But then a few years later, Greg Moore realized that there is a different formulation, which is much nicer in some sense. So here, a bit more. So what he says is that the absolute value square of the center charge function has a stationary point at C equals C star, which depends on gamma in twiddle, with the additional condition that the center charge does not vanish at this point, if and only if the Poincare dual of the cycle gamma is in H3 0 plus H03 intersect with H3 C. So we'll discuss this equation a little bit later, so I'll give it a name star. And moreover, if C star of gamma exists in the interior of M, then it is a local minimum. So actually, I prepared a proof of that statement because it's really simple, and all you need is what I wrote here. It follows from what I wrote here. But for time reasons, I skip it, and maybe I'll tell it at the end. But now let's try to understand what this equation star means. So, interpretation of star. So let's call the Poincare dual of gamma by gamma hat. Actually, do I need? Yes. Do I need that? No, not really. I would have needed it for the proof. So the interpretation of equation star. So we only need to look at what this here means. What does this really mean? So let V C be the first part. So the sum of H03 and H30. So this is a complex two-plane in H3x with complex coefficients. Now let's look at VCR, which is H03xc plus H03. Actually, too complicated. So it's VC intersect with H3xr. Now, since H30 is generated by omega and H03 by omega bar, if I take the intersection with the real cohomology, we get a real two-plane in H3xr. So finally, if we intersect VCR with the cohomology lattice, we get a lattice, and actually I should have called it maybe. Okay, let's do it. A point S Z in M is an attractor point of rank 1 or 2 if the rank of this lattice is 1 or 2. So generically, you would expect that this lattice has rank 0 because you don't expect any real plane to intersect a given lattice. But then you can turn it around a little bit, the real plane, and then at some point it will hit a lattice point, and hence at least a one-dimensional sublattice. And if you're fine-tuning the plane even further, then you might be lucky and hit even the second lattice direction. So from this naive argument, you expect that rank 1 attractor points should be quite frequent, and they are. It's relatively easy to find, and actually they are expected to be dense in M. Now, rank 2 attractor points, on the other hand, turn out to be very rare. So rank 2 attractor points are rare. So the first non-trivial example, by non-trivial I mean for a moduli space which is not a Shimura variety, was given a few years ago by Candelas, De La Osse, Elmi, and Van Straten in 2019, and since it's so by now I know of about maybe 20 to 30 Calabi Yaus, which in their moduli space have 1 or 2 such attractor points of rank 2. So there are really a few given the number of Calabi Yaus we know. So there is, on one hand, by trying to find one is very hard. So Candelas et al. Conjecture that probably there are finitely many such points. But there is another interpretation, which is that, actually I forgot to say that. Yeah, I should have mentioned that before. So if you look, there's another way of looking at the equation star. which is just by writing down explicitly the equations to be for this cycle, for the Poincaré rule of this cycle to be in that lattice. And these turn out to be 2H1 plus 2 real equations for 2H21 plus 2 real variables. So in general, you really expect isolated points. And from the mathematical point of view, if you want to give what this definition means is that it's a very special kind of what is known as a Hodge locus. And recently, Klingler and his collaborators have been studying lots of conjectures on the density or finiteness of Hodge loci. And they also considered this case, and their general conjectures imply, if they're true, also imply that there would only be finitely many such points. Okay, now let's go on and look a little bit more about what this means for from the point of view of Hodge theory. So we have this lattice lambda c, and then we can tensor it with the complex numbers, and obviously what we get is H30 plus H03. Then we can look at the orthogonal lattice with respect to the polarization Q that I introduced before, and then this must be H21 plus H12. So what we see is that lambda c plus lambda c orthogonal forms a lattice inside H3 of C, and one can check that it is of finite index. So therefore, we conclude that if we look at the rational cohomology, it splits into let's see. Okay, let me write it like this. Yeah, let me write it like this. So this means lattice tensored by Q plus lattice tensored by Q orthogonal. And let me call this H1, and this is H2. But since we have this, this decomposition into Hodge structures, this means that H1 is a Hodge structure of weight 3 and type 1, 0, 0, 1. And H2 is a Hodge structure also of weight 3 and type 0, 1, 1, 0. So here, let me make, actually, do I need that at this point? Okay, yeah, let me make here the simplifying assumption. It's still it's simplifying assumption that H21 of X is 1. And then if we tensor H2 by the Hodge type structure Q1, then we get a Hodge structure of weight 1 and type 1, 1. So this means that this is the Hodge structure of a rigid Calabi Yau threefold. And this is the Hodge structure of an elliptic curve. So at these attractor points, one can characterize them differently from a Hodge theoretic point of view. Namely, at these attractor points, we have a splitting of the Hodge structure into the Hodge structure of a rigid Calabi Yau threefold and the Hodge structure of an elliptic curve. Now, especially the elliptic curve, but also the rigid Calabi Yau threefold, they ring a bell, namely modularity. So let's come to the promised interlude on modularity of elliptic curves. So I briefly want to review a few fundamental results in the modularity of elliptic curves, which may be relevant for what we are doing here. So first, we of course have the theorem of Wells, Taylor, et al., which says that if E over Q is an elliptic curve, it is modular, which means that there exists weight 2 modular form for gamma 0 n, where which is Hecke eigen. Oops. Which is a Hecke eigenform. N is the conductor of E. Such that the L function of the elliptic curve agrees with the L function of the modular form. More practically, it means that the complex points of the elliptic curves are given by a lattice lambda f, where the lattice is determined by the modular form f, which can be described as the integral of f of c dc over the homology lattice of the modular curve gamma 0 x0 n. So more concretely, we have a modular parameterization of the elliptic curve. So that's a map from the modular curve into E, which sends the point represented by tau in the upper half plane to the point p tau, which is the period integral from infinity to tau modulo the periods, and infinity is sent to 0. And theorem of Manning says that lambda f actually can be written as two periods obtained by f, where omega f plus minus are the so-called periods of the modular form f. So that's one result I'm interested in. Yeah. Now let's still talk about elliptic curves, but and still about gamma 0 n, but let's look at a completely different point of view. Namely, let's look at families. So let E over x0 n be a universal family. Of elliptic curves with cyclic subgroup of order n. Then there exist special points in x0m. Let me again represent them by a point in the upper half plane, so-called Heckner points, for which the fiber E over the point tau has an endomorphism ring over a field, number field, which is bigger than the integers. So these two points have two properties. One, they're rational quadratic integers, so they live here. And furthermore, the J function at these points takes value in algebraic integers. Another property is if L is a number field and E over L an elliptic curve, and assume E has complex multiplication by the ring of integers of some subfield K of L, then the L function of E or L factorizes where CL is so-called Hecke-Größen character. So it's not really important what this is, but the main point is that at these special points we have a factorization of the L function of the elliptic curve. So this ends the interlude on elliptic curves, and one could ask the question: which properties that we've now reviewed from the elliptic curves generalize to Calabi Yau threefolds, and how? And so the idea is to compare these attractor points with the Heckner points. And the question is, are attractor points a generalization of Heckner points, or are they do they have entirely different properties? So so before we do that, let me here we have a relation to elliptic curves, but here we had a relation to rigid Calabi Yau threefolds. Now, for rigid Calabi Yau threefolds, we are also fortunate, namely, we have also a modularity theorem. So, modularity.
Hi, Emanuel.
Yes.
Can you show that all attractor points are defined over Q bar? For example, for elliptic curve, for CM elliptic curve. Can you show that all attractor points are defined over Q bar?
No. So what one can show is that, so first of all, we only have examples, and all the examples are defined over Q bar by construction.
Okay.
But there is no general statement that such an attractor point in one of the various definitions I have given must be defined over Q bar.
Yeah, but maybe the reason is that really the attractive point doesn't fit into the definition of the Hodge locus. whereas this CM elliptic curve, you can fit it into the definition of Hodge locus, but the attractive
Yeah,
points-
so the as far as I understand the work of Klingler, he is able to fit the definition of the attractive point into the definition of the Hodge locus.
Okay, maybe some general. Okay, I have to look at it. Thanks.
Okay, so modularity for rigid Calabi Yau threefolds. So here we have the theorem due to Gouveia, Yui, Dioleffe. So take X over Q, a rigid, smooth, projective Calabi Yau threefold. Then X is modular in the sense that we have the following. There exists a modular form of weight 4 for gamma 0 n. Write this differently. There exists an n and an f Hecke eigenform. Such that the L function of the middle cohomology of X agrees with the L function of F. So there are kind of, so this statement looks very similar to the modularity for elliptic curves, but actually it's weaker in at least two ways in my understanding. So first of all, there is no way to determine n a priori. So you have to do the point counting on X over finite fields, and then you can fit the modular form, and then once you have the modular form, you can determine under which gamma 0 n it transforms. The only thing it's known is that n divides the bad primes, but that's all. And the other thing is here we had this beautiful modular parameterization. So to my knowledge, this modular parameterization is also not known in general. Okay, but at least we have, and that's for enough for us, we have this statement here, which will be relevant, and we have this statement here for the elliptic curve. So let's now go back to the attractor points. So again, for simplicity, we assume that H21 of X is 1. So then there is conjecture. I think it's due to, let's say, originally due to delinear in a very general setting, and then more concretely, I think I have to mention the names, Gorishev, Sagier, and then in even more concrete ways, Sagier. Which says the following. So let's pi z be the period matrix of our family of Calabi Yau threefolds. in an integral symplectic basis. So that's important. Then let's pi star be the period matrix or a period matrix of the member X at attractor point C star. And then, since they're solutions to differential equations, we know that they're related by analytic continuation, and let's denote the continuation matrix by M. And then the conjecture is there exist integers n1 and n2, modular form of weight 4 for gamma 0 n1, a modular form for weight 2 for gamma 0 n2, and a choice of bases. For H3 X Z, so an integral basis such that the matrix M star has the following form. Oops. Omega F plus, omega F minus, eta F plus, eta F minus, 0, 0, omega G tilde plus, omega G tilde minus, omega eta G tilde plus, eta G tilde minus. Where omega F plus minus are the periods F in the way I introduced them before. So Manin's result is applies to any weight of module forms, not just weight 2. Then eta F plus minus are the so-called quasi-periods of the meromorphic partner, or of a meromorphic partner. F of F. And similarly for G. And moreover, the L function of X at the attractor point factorizes into the L function of F and the L function of G. So this is the conjecture about the arithmetic of these attractor points. And so in order to verify the conjecture, or at least to, so mathematically what's behind this conjecture are the Hodge conjecture and the Tate conjecture. So if those are true, then this conjecture here is true as well, except for maybe that one would like to have a recipe how to determine N1, N2, F, and G. But since we don't have these conjectures, what we can do is we can look at examples and at least as a first step, verify whether this conjecture makes sense numerically. So this in the end means that we have to compute two matrices. So one matrix is very easy to compute, namely this matrix here is easy to compute because we know it's easy to determine this period matrix. It's easy to determine this period matrix because we can solve the corresponding Picard-Fox equations. So that's easy. And then what's a bit more involved is to determine this matrix. And in particular, our contribution to this conjecture is to make these two numbers and these two numbers specific. So we gave a prescription first of, so first we define what the meromorphic partner F is. So it's a meromorphic modular form of weight 4 or 2. Which has which is also a Hecke eigenform. However, it's not well defined in the sense that we can always add multiples of little f to capital F, and it's still a meromorphic partner. And this indefiniteness is reflected in this statement here by choice of integral basis. Moreover, the pair little f and capital F forms a Hecke eigenspace on a multiplicity 2 decomposition of the meromorphic modular forms of gamma 0 n. So in our work, we make all this very precise, and we give prescriptions how to compute all of these numbers. So first of all, how to determine f and g, capital F and capital G, given little f and little g, and then how to compute these numbers here. And then we have two matrices, and we can verify them. So the equality and so the main difference, the main difficulty is that the basis in which one determines this matrix does not have this form here. So we have to find for integral linear combinations of these numbers, which is then kind of numerically quite involved and not very straightforward. So, but we have done this for examples. And of course, the first class of examples that one thinks of is hypergeometric families. Of Calabi Yau threefolds. So let me review a little bit what these are. We assume that the Gauss-Manin connection has exactly 3 regular singular points. So we can write M as P1 minus 0, 1, infinity, or in other words, M bar is P1. And then the corresponding Hodge structures have been classified by Doran and Morgan. So there exist 14 Q variations of Hodge structures of Hodge type 1, 1, 1, 1, such that the monodromy around 0 is maximally unipotent. The monodromy around 1 is of conifold type. So TC, focal monodromy. of connection around C and bar. And so if we look at flat sections of our flat connections, what we get is a hypergeometric differential equation. Which is of the form theta to the 4 minus C times the product I from 1 to 4 theta minus alpha I to pi equals 0. So here theta is C over dc, C a local parameter. Zero and bar. And so what the theorem gives is all the 14 possibilities of the values of alpha. And so we have now a more specific conjecture. Which is that if you take alpha to be 1/3, 1/3, 2/3, 2/3, then there is an attractor point at z equals -1, 2 to the 4, 3 to the 3. We can take n1 to be 180 and 2 equals 36. And another possibility is, oh sorry, now I mixed the two examples up, so let me change this. So this is 1/4, 1/3, 2/3, 3/4, and here it's the one I wanted before. So here an attractor point is at -1 over 2 to the 3, 3 to the 6, and n1, n2 are 54, and explicitly given F, G, and G. So for these values, this conjecture holds in the sense that we have numerically verified to very high precision, like thousands of 1,000 digits. Okay, essentially I'm done. Let me maybe make one more remark. So this is kind of the attractor point story. Originally, we were looking at different points. So, and this is also in the paper. So here here in the theorem of Moore, to prove this, we have in the interior of M twiddle, which means that the metric should not be degenerate at an attractor point. However, it turns out that the conifold point, which is a singular point of M, so it lies in the boundary, and at this point the metric has a singularity, it goes to infinity. can also be thought of as a degenerate attractor point. And so originally what we were looking at was this conjecture here for these conical points. In those cases, we actually have a different behavior. We have to replace the Hodge structure by the limiting mixed Hodge structure, which can be decomposed into pieces of pure Hodge structures. And one piece is again the Hodge structure of a rigid Calabi Yau manifold. And this was already known to Schoen in '86. And he was the first to compute an N and an F in the context of rigid Calabi Yau threefolds. And so we've extended this to all 14 hypergeometric families and shown that there is a similar decomposition like this one, and where there is only one two-dimensional piece. And for those, the L function of the singular Calabi Yau or Calabi Yau resolution of the singular Calabi Yau agrees with the L function of the modular form given by these periods. Okay, that's all I wanted to say. I think my time is also up, I'm happy to answer all your questions.
Okay, thank you, Emanuel. Jin, can you stop recording?
Yes.